Okay, so last time we talked about all these definitions. I think there's like 30 of them total, of which we did like 28 last time. The two that we didn't get to are bipartite graphs. And so bipartite graphs are, so bi means two, partite means parts. And so these are graphs that we can split into two separate parts. So if we say that one part is A, the other part is B, we can have all these vertices in A and all these vertices in B, and we can connect edges between the two parts. So like, you can have this and so on. So the edges only go between these two. And within each part, there can be no edges among the vertices of that part. So that means all the vertices in B cannot have edges. There can't be any edges within B. There cannot be any edges within A. And then the other part of that, the other thing that goes along with that is what's a complete bipartite graph, which is just a bipartite graph where every possible edge is present. So like there has to be an edge from each thing in A to each thing in B. And we denote this K and then sub n comma m. And so n is the number of vertices in A, so n is equal to 3. M is equal to 2 because there are two things in B. Okay, that's bipartite and complete bipartite. Now we get to do something fun. Okay, I'm gonna record this small bit. I have a graph here. Can you trace every line in this graph without backtracking and without lifting your pencil? In your
In my mind. And does that have to go over every edge?
Yes, every line in the graph.
Can you hit a vertice more than once?
Yes.
Perfect.
You can hit a vertex more than once.
Should I?
Yeah, so
It's possible.
okay, do you want to draw it?
I can try. Wait.
Oh.
Hang on.
Yeah. All right. So this game is in fact representative of a property of some graphs. And so the property is called this word, which looks like hold on. Euler. Okay, so this was invented by a guy with this name. The guy with this name, his name is pronounced Euler. Euler. And so this is an Eulerian path. So it's pronounced like Euler. I don't remember what nationality he was. Does anybody want to look it up? Yeah?
Swiss.
Swiss?
I think so.
Okay, yeah. So there you go. So he has defined this kind of graphs, named it after himself, called Eulerian. And this is the kind of graph where this property holds, where we can find an Eulerian path or Eulerian walk, depending on how we call it, where, let me add a new page over here. So we can call it an Eulerian path or a walk or possibly a trail. And the difference between these three words is simply whether or not we can like go back on edges or repeat vertices as we're going around the graph. And so I think trail is generally what we call it. Sometimes you might call it a cycle. That's not how you spell cycle. Except I don't like calling it a cycle because there's the possibility to repeat vertices. And so to me, having a cycle means you start somewhere and you go around and you don't repeat anything. Okay. The way that so he started this process because, let me see if I can draw this correctly. There's there, and there. I think I've got that. And so let's find blue. And so he lived in the city of Königsberg. Of which there were 7 bridges. And so the edges in this case are the bridges, and the vertices are the land masses. And so his question was, can I start somewhere, walk around the city, cross the bridges exactly once, so I can't walk across the same bridge twice, and can I return to my starting point? So, spoiler alert, the answer is no. And so let's talk about exactly why. So we've got a theorem. I did not plan this well. So we've got a theorem which says that, so we're going to let G be a connected graph. And the language in the book is on at least 2 vertices. We have some restriction for the size of the graph. And then we've got 3 statements. If G contains no vertices of odd degree, then G contains an Eulerian, the book calls it circuit. I think I will accept circuit because, so for this particular one, it's a question of starting somewhere, going out, and coming back to the same point. So circuit in that sense where we start and end at the same place, but not necessarily fulfilling the definitions of cycle where we don't backtrack at all or there's a possibility to use multiple vertices. So G contains an Euler circuit, and we say G is Eulerian. This is a property of this graph. So the graph that you drew over, that's an Eulerian graph because we can come up with this circuit that does that. Property 2, if G contains exactly 2 vertices with odd degree. What's degree again?
Edges.
Yeah, so the number of edges that a vertex has. And so the first case is if there's no odd ones, if all of them are even. The second case, if there's exactly two that are odd. So if this is the case, then G contains an Eulerian path that begins and ends. I need more space. So that begins and ends at those vertices. So we can find where are the two that have odd degree, start at one, work your way around the graph, end at the other, such that all of the edges get covered. Third case, if G contains more than two vertices of odd degree, then G doesn't have either one of those. Path or circuit. The one thing that's not in the book is that if it has those exactly two vertices of odd degree, we call the graph semi-Eulerian. So if all of the vertices are even, then it's Eulerian. If there are exactly two vertices of odd degree, then it's semi-Eulerian. And if there's more than that, then it's just not. Okay. Okay, now I've forgotten. One of these is Hamiltonian, the other is Eulerian. Let's talk about Hamiltonian first, and then we can solve that problem. Okay, so Eulerian is all about covering edges. And so this is analogous to if I am a mailman, I have to go and deliver mail to on every street in the city. If it snowed in Moraga, we would need to have snow plows that plow every street so that people can drive, right? So that's Eulerian. Eulerian is all about edges. Hamiltonian, however, is about vertices, where if we have some graph that, okay, trying to think of an example that's not traveling salesman. I think traveling salesman might just be the answer. So let's say I run a delivery company in the Bay Area. And I have to deliver things to every area. So like I have to go to North Bay, I have to go to East Bay, South Bay, and San Francisco and the peninsula, right? I have to go to everywhere. How can I do that? By taking as few roads as possible. So like I want to, maybe I go up to North Bay and then down and around and just do a cycle, or maybe I cross the bridge and go into the East Bay first, and then I cross the bridge, that bridge, from Fremont to Palo Alto, right? So I've got options. This sort of problem where I need to visit each location, as opposed to I need to travel across every bridge between these areas, where I need to travel between every location at least once. This is a Hamiltonian problem. Okay, So a Hamiltonian path is a path that visits each vertex of G exactly once. And a Hamiltonian cycle is a true cycle, which is a cycle containing every vertex of G. And since it starts at one point, ends at the same point, so like if we start in the North Bay, we've got to go home at the end of the day. And we want to visit each place exactly once because we don't want to have to, if we're, let's look at a place name. Like if I'm driving through the city, I don't want to drive through the city again. Like that's a waste of my time. So yeah, so visit each location exactly once. That's a Hamiltonian cycle. There's a theorem about this. 9.4 by someone perhaps called Ore. Which says that if G is simple with n greater than or equal to 3, this is a good time to mention that traditionally, this is something that I have been hounding my 222 class over, where n is what? The size of the input. And so typically when we talk about graphs, we talk about n as being the number of vertices. So whatever object we're representing, if it's regions in the Bay Area, if it's cars on the road, or if it's intersections for where we have to snowplow, n is the number of objects, is the size of our input. So if G is simple and see, I've never played Minecraft, so if the degree, wait, no, where did I get that? Okay. If for every pair of non-adjacent vertices, we'll call them V1 and V2. And what is the condition? If the degree of them, if we add it together, is greater than or equal to n, for every pair of non-adjacent vertices, then we say G contains a Hamiltonian cycle. And there's other corollaries of trying to whittle it down of how can we be sure, like what sort of qualities can we place on G to say that it contains a Hamiltonian cycle? So two main qualities, Eulerian, Hamiltonian. Eulerian starts with E, it's talking about edges. Hamiltonian is talking about vertices. H does not correspond to B, so unfortunately. So the thing about Eulerian is it's fairly easy to, so like we can look at the degree of all of the vertices and say, yes, for sure, that is Eulerian. We don't have any simple statement like that for Hamiltonian. And that's because finding a Hamiltonian path or Hamiltonian cycle in a graph is NP complete. What is NP complete? It's basically really, really hard. So there are different categories of problems we can solve in computer science. Some of them, and so like when we talk about algorithm analysis of this algorithm takes linear time, or this algorithm takes polynomial time, quadratic, or something like that. We can write that down and say this is how much time it takes in proportion to the size of our input. There are some problems that are non-polynomial, which we call NP, and this basically corresponds to something like exponential, where it's really, really hard to do this. And if you figure out like a polynomial way to solve the Hamiltonian cycle problem, then a few things have happened. You've earned yourself an instant PhD, and you've also like broken every assumption that computer scientists have about problems that we can solve. So like you've probably broken encryption. Like it's wild. So people have been arguing whether the set of problems that can be solved in polynomial time correspond to the number, like, can we find a polynomial solution to any of the things in NP? The assumption is generally no, but it's an open problem. Nobody knows. So that's why we don't have any nice algorithm or definition for that. It's not that you can't find a Hamiltonian cycle in any graph. You definitely can. It just takes forever. So because it's non-polynomial, no one's figured out a way to do that in polynomial time. Okay. The only other thing I have to tell you is about weights in graph. So you can have unweighted graphs. So like any of these are unweighted because there's like, it's just dots and lines. There's no numbers in there. But we can add numbers to our graph where we can say, like, maybe this is the amount of time that it takes to drive between like St. Louis and Memphis. Maybe it takes 8 hours to do that. 8 minutes. I feel like that is not realistic, but it could be like, or maybe it costs $8 in gas to go from one place to another. We can add numbers to that and make it mean whatever we want. We can also say, so I think I opened up a random number generator when I made this graph and put numbers on it. So maybe it takes 90 minutes to drive from the North Bay to San Francisco, 50 minutes to drive into the peninsula, 35 to drive into the South Bay, etc. So we can put numbers because graphs at their core are just relations. So if we find out here's what the relation, like here's what the objects are that we want to relate to each other, and then we define here's what that relation is. If we want to add numbers, if that brings meaning to it, then we can. So like if we want to represent it with distance, then that's fine. And we can add those numbers. Otherwise, if it just matters that there is a relation, so like one of the examples is like friends on Facebook, or nobody uses Facebook anymore. So maybe like followers on Instagram, right? If two people follow each other, then there's no numbers needed for that. We can just say there's an edge. They follow each other. Something that the book has not talked about, but which is important to know, is that we can have what we call directed graphs, where currently we've been working with undirected graphs, which is just there's a line between two dots of this is a relation between two objects of person A is following person B on Instagram and vice versa. But it could be that maybe person B is famous, and so A can follow B, but not the other way around. So this is a directed graph. It's also sometimes called a digraph, which is just because DI is short for directed. And so we call it a directed graph or a digraph. Okay, so I know I said maybe Monday for the problems, but I think I want to, so we have about 10 minutes. So I want to leave you time. You can either play the game, which, so this is a game that if I open it in a new window, my job is to create an Eulerian path or Eulerian cycle. So I can, I think this is easier on a phone.
And also if you save them.
So there, I found a path, and then it rates you 3 stars no matter what you do. So this is a star, and I can go around. Hooray! Also 3 stars.
Victory.
Ah, keep going. Hooray. So this is all practice in finding an Eulerian path or cycle, so you can play around with this if you want. You can also, what I would recommend is start the homework and look through it. Let me know if you have questions. And on Monday, so we talked about traversing edges. Monday, we will talk about how to actually apportion our fish tanks so that no fish in the same tank hate each other
Fish.
or eat each other. That's right. That's what the problem was. All right. Any questions? Yeah.
Is our final?
Is our final cumulative? This is a great question. Do I have the answer yet? No.
What I'm hearing is a make.
Yeah, that's correct. There will be significant questions on graphs. It's also 2 hours long. So we have more time than usual exam. So my initial thoughts are probably half on cumulative stuff, and the other half on graph stuff.